Hi folks, welcome back to the 6.2 Disc and Washer Method practice. In this video, we're going to take a look at question number 2 from the practice. Question number 2 says find the volume of the solid of revolution generated by rotating the graph of f of x equals x squared plus 1 over the interval of -1 to 1, and we're revolving it around the x-axis. So I can actually start here by drawing in my axis of revolution. Okay, so my axis of revolution, and the equation for that is y equals 0. Okay? Now I'm going to draw in my curve. So x squared plus 1 is a parabola that is moved up 1. So I can say this is a parabola, and I'm moving it up 1 unit because of that plus 1. Now what that means is my vertex will be at 0, 1, and then from there I know that 1 squared will give me 2. If I plug in -1 for x, I will get 2. And I can connect these to get the bottom part of my parabola. And I'm going to mark off my bounds. So I'm going from -1 all the way to 1. All right. So like the last video, I'm going to suggest that we sketch our reflection so we get an idea of what the whole shape looks like when we've revolved it. So I have a point down here at -1, at -2, and at -2. Okay, and that means that my bounds would kind of come down here too, and this would be half of the shape that I'm looking at. Now, because I am revolving these around an axis, I know that I'm going to end up with a cross section of a circle. And the area formula for a circle is pi r squared. And so what I want to do is draw in the radius. So the radius, like one example would be from here to here. Another radius might be from here to here. And another radius might be all the way out here. But all 3 blue lines represent radii of circles or slices of this graph. All right, so now that we have an accurate picture, we're going to go ahead and set up our integral. So we know that volume equals the integral of the area, and then in this case, we're going to do dx. Now let's find our bounds. I know it goes from -1 to 1 of pi, and my radius is defined by my function x squared plus 1 squared. Okay, so this is my pi is from here, and then the radius gets squared because the area formula is pi r squared. All right, now I'm going to go ahead and use a shortcut that I think is generally helpful. And what that is I notice that this shape is symmetric. So I'm going to go ahead and find the integral from 0 to 1, and then I'm going to double it. Okay? So that's going to give me the integral from 0 to 1 of pi x squared plus 1 squared dx. All right, so let's take out our constants. Let's FOIL out that x squared plus 1. 2 pi, the integral from 0 to 1 of x to the 4th plus 2x squared plus 1 dx. All right, let's take the antiderivative. This will be 1/5 x to the 5th plus 2/3 x to the 3rd plus x, and I'm going to plug in 1, and I'm going to plug in 0. All right, let's plug in our bounds. 2 pi 1/5 times 1 to the 5th plus 2/3 times 1 to the 3rd plus 1 minus 2 pi times 1/5, 0 to the 5th, plus 2/3, 0 to the 3rd, plus 0. I'm going to do a double check, but everything in the last one should give me 0. And that's the beauty of using symmetry, because now I can focus on simplifying the part that I have with numbers. All right, so this gives us 2 pi 1/5 plus 2/3 plus 1, which will give me 2 pi, let's put everything over 15. So I've got 3 over 15, I've got 10 over 15, and 15 over 15. And this should give me, let's see, 3 plus 10 plus 15 is 28. 28 times 2 is going to be 56 pi over 15. And 56 pi over 15 represents the volume of the shape that we get when we revolve it around the x-axis. Now keep in mind that this is a 3D shape like we saw in our lecture, but because we're drawing it by hand, we're drawing sort of a 2D version of the 3D shape. All right, folks, that's it for question number 2. Come on back for question number 3.